And with that, we are already at the last talk in our track today. We are joined by Ivica Kolenkas. I hope I pronounced it correctly because he sent me how to pronounce it, so I hope I did it right.
Yes, you did.
So Ivica is a system engineer and he works at Bestseller and does some Python coding by night. So today he will show us, I think, the most famous example of using serverless technologies using Lambda resizing images, but reinvented using step functions. So Ivica, take it away.
Exactly. So thank you, Martin, very much for introducing me. I hope you cannot hear how my heart is pounding. But since you did introduce me so well, I will just jump straight to the point and briefly introduce you to the company I work for. So Bestseller is probably one of the biggest companies that you never heard of, and essentially it is a family-owned fashion company from Denmark. And if this was a face-to-face event, I would usually ask for a show of hands with the question of how many of you have heard of Bestseller, and usually 2 or 3 people would raise their hand, and that's completely understandable. In the end, we really do not mind if you don't know of Bestseller, as long as you know about our brands. So, as I said, Bestseller is an online fashion company, and we are selling clothes from 16 different brands all over the world. And one thing that you need if you want to sell clothes online successfully are high quality product images. And because of that, the title of my talk is Resizing Thousands of Images Daily, One Step at a Time, which should show how AWS and more specifically how Lambda and step function services are helping us to get thousands of images every day from our photo studios to our customers online. So as I said, Bestseller started its online business back in 2010, and ever since then we used a software product that would resize our images. But of course, it was bringing us a lot of pain over the years, mainly because it took more than 90 minutes to process 30 images. It usually broke down twice a week if you would queue more than 1,000 images for it. And then in order to make it work again, you needed to contact a remote IT department, and then they would, reboot 6 VMs, make it work again and whatnot. And by the end of the year, we would receive a bill of about 15,000 euros for licenses and support. And naturally, Bestseller as a company really wanted to grow in every way possible, and our image resizing solution also needed to grow, old, and die. So having said that, we, the tech department of Bestseller, jumped on the resize images with Lambda train back in 2018, and we set out to build our own image resizing solution with Lambda and with Python. And since we were rookies with both Lambdas and Python, we ended up with a total of 3 Lambda functions. One of them was verifying the naming scheme for each image. Another one did the actual resize and moving of the resulting image to an appropriate S3 bucket. And there was a third function that was used to delete images when needed. And this is how it looked like, and this is how it worked. So a photographer or someone else that works at the studios would upload an image to an S3 bucket. That triggers an event that would start a Lambda function, and the Lambda function would validate the name of the file. So if the file name was correct, then it moves the image to another folder and another Lambda gets triggered, and you get the picture. But if the file name was wrong, nothing would happen. We would usually get a support ticket maybe tomorrow, maybe the day after, where someone would come to us with a question of what happened to our image, such and such. Why is it not available? And then we would turn into Indiana Jones and do some log archaeology, and it was painful. It all really reminded me of this movie, See No Evil, Hear No Evil from the 90s, where the premise is that one guy is blind, another one is deaf, and they witnessed a murder. So long story short, it's a funny movie. You should definitely see it. But it also perfectly illustrates the application that we came up with back in 2018. And talking about the application, It had big artifacts, yes, and it had long timeouts, definitely. But this was not the main issue of the application. The main issue with it was that it wasn't providing any feedback to the end user. Yes, of course, there were errors in CloudWatch, and we do have monitoring and all of that, but the end user is not aware of it and should not be aware of any of it. So for us, it was really obvious that a couple of things needed to change and some things needed to happen. First thing, we needed some fast and clear feedback for the average PC user, for the photographer in the studio. We also needed to resize images to different sizes, and in order to do that, we would need to change our code drastically. And since it was already 2020, we decided to do some code cleanup and some infra housekeeping. So keep in mind, when I say that we need fast and clear feedback, I really mean emails with error messages. It's that simple. Everybody can read emails, and we can also convey whatever message we want to with emails. But it also meant that we needed to update the existing code base to do all of this, which was not something that I was really keen on doing. So we decided to make these three points into our main objectives and to just go from there. Luckily, I read something about step functions, and I thought this was the perfect opportunity for us to convert the existing architecture into one or more step functions. So what are they exactly? I'm going to quote badly the AWS product page, which says that step functions are a serverless function orchestrator that combines AWS Lambda and other AWS services to form applications. They also offer you a visual representation of the execution and are completely event-driven. And each step in your application executes in order of your choosing. So you control what happens and how it happens. Every step function, of course, is composed of multiple tasks, which are shown as round rectangles here on the slide. And each one of these tasks can be either a Lambda function, it can be an ECS container running, it can also be a direct query to DynamoDB, and since a couple of days, it can also be a direct Athena query. And of course, much, much more. And if you want to create step functions, you need to learn a little bit about their JSON-based language, which is easy enough to learn, granted, but it's also versatile enough and allows you to do all sorts of business logic rules. The first one being parallel execution. So for example, if you need to run certain tasks in parallel, where the whole block will fail if any of them fails. And this was really perfect for us. At other times, you may need for your task to wait, for example, for a specified number of seconds or until a certain timestamp, so you can have all sorts of timeouts. And if you need to perform some sort of a for each loop, dynamic parallelism has you covered there because it allows you to run identical tasks in parallel. For example, you can process 10 orders at the same time because the order processing task is the same for each order, hopefully. And if the flow of your application is not completely linear, step function language does support branching, so you can go to a different task based on a choice field. And of course, last but not least, each task does support error handling. So for anyone who is tuning in right now, please keep in mind that I will be saying the word execution very often from this point on. Everything is, of course, all right. It's just a step function term. Talking about executions, all the features that I mentioned so far are really, really nice, and they allow you for great versatility. But what we really found most helpful in our use case were the execution history and visualization features. So one thing where execution history is really great is when you need to find out what happened. So something broke and you need to deep dive into it. This is, of course, very different from using plain old lambdas, since they don't have the execution history, and you have to rely on your logs and your metrics to figure out what broke and when. This, of course, doesn't mean that CloudWatch metrics and logs are not useful. They will definitely come in handy once you pinpoint what has failed. But it's much easier to pinpoint what failed with the step function execution history. That is because you can easily filter the executions. You can search for a specific execution by name, or you can just say, show me all the failing ones. And this feature is really amazing. So for example, when a support ticket comes for us with a specific image name, we can just search for it and we can explore from there. And this is where those logs and metrics will come in handy, because you actually found the haystack. Now you just gotta find the needle. Luckily, step functions will also help you find the needle, because if you click on the failed execution, they will show you which exact task has failed. They will also include the link to a Lambda function that has failed this, which is the task. They will show you CloudWatch logs for the function. And also they will show you the input and the output for the task, the actual event that was passed on to the task, which helps you to write better unit tests or to write more unit tests so that you can cover these specific cases that have failed. And talking about failures, of course, exception and full traceback are also available through this simple console. Now that I mentioned tracebacks and exceptions, let's see how error handling is done with step functions. The language itself supports some generic errors, such as the timeout error, permission error, and the catch-all error, which is, of course, going to match any error that happens. And in the case that any of these does happen, you can define a retry mechanism that is going to do something meaningful. So let's look at an example of a retry block. So this retry block is going to happen when a task essentially times out, and it will retry the task. The first retry is going to happen after 3 seconds, and the second retry is going to happen 4.5 seconds later, because we have the backoff rate defined. Another example on how you can handle errors is using a fallback state with a catch field that is very similar to the retry field. And in this example shown in the slide, we can see that we are catching a generic and unhandled Java exception. And if such an exception is caught, the flow of our application is going to be redirected to a different task that is called handle exception, which can do something meaningful with the error that has happened. Another area where these fallback states really shine is the ability to catch your own custom exceptions, which we did use heavily in our image resizing product. If you remember, one of the main reasons for us to do the rewrite was to make the whole application more verbose and send out feedback to its users. So what we ended up with is we created a custom exception, and we paired it with a fallback state that was catching this specific exception. And then it would redirect the application flow to the task that was called handle validation error. And this task would do something that we wanted to do in the first place, which is essentially send emails. And with this task, with this step inside of a step function, we can send emails like this. This is a simple email with a simple message, and it conveys to the user that uploaded the image, it conveys the message very clearly and very quickly, because it takes less than 30 seconds from uploading an image to receiving such an email if something is broken, of course, which means it's fast and it's clear and no more support tickets for us. So objective 1 was achieved. Another set of objectives that we set for ourselves was to do some code cleanup and some infra maintenance. And as you can see, the graph on the left shows the old process, and the graph on the right is the new one. And the graph on the right has exactly 5 times more Lambda functions than version 1. And it more than doubles the amount of AWS services that we used in general. So you might say that it is a bit more complex. It definitely is, but it did allow us to achieve objectives 2 and 3 with ease, relatively speaking. And finally, let's explore how much it costs us to run this. So the graph that I'm showing here is for the month of September. This is our production account. No numbers have been adjusted for the sake of this presentation. It's obvious from the graph that this app costs us on average $6 per day, which comes approximately to $188 per month for the whole month. And this, of course, includes all the S3 cost for storing almost 2 million images that we have, which is by far the biggest chunk of total cost. So in other words, it costs us approximately $0.002 to resize and store one single image. Exactly. We saw that the costs of the application are pretty low, but were the complexities and challenges also low at the same time? Let's find out. One of the first challenges that we met was how to trigger this step function from an S3. Remember, a user uploads to an S3, so we need to react to that event. And one of the solutions that I found online was to use CloudWatch logs and CloudTrail. And I didn't like the solution, first of all, because no one in our company was using CloudTrail at the time, and it would be hard for me to hand over the project and explain what CloudTrail is and how it works and whatnot. So once again, we decided to roll something homegrown, and the solution that we came up with included AWS services that most of the company is familiar with and that we're already using. And it also solved the issue of losing S3 events in case of downstream failure, because all those S3 events were accumulated with SQS. And then a Lambda function would be triggered by SQS, which would in turn trigger the step function. So without even knowing it or planning it, we created something that will both help us and hurt us at the same time in the future. So let's talk about these. The most obvious thing that we gained as a benefit was keeping all the S3 events in case of downstream failures. But next to that, we could also control the input for each execution. We could basically control each event. And this allowed us to insert things such as correlation IDs into each execution payload. And then this correlation ID gets included into the application logs. So when that log archaeology does need to happen, it's much easier to trace one event through a series of functions and a series of steps in a step function. Other than controlling the input, we were also able to control the name for each individual execution. And step functions require these names to be unique, of course, but we also needed them to be searchable at the same time. So the combination that you see on your screen was born. Essentially, the UUID is there to guarantee uniqueness, while the image name is really helping us when we need to search for a specific execution in case of problems. One of the things that hurt us is something that we completely forgot about, and you cannot really see it until you go to a scale, to some scale, and that's the at least once delivery of S3 events. Sometimes, rarely, but sometimes, S3 would deliver 2 events to SQS, which would trigger 2 executions for one single image. And this, of course, should not be a problem if the downstream process is idempotent, but it wasn't at the time because of some business decisions. So we needed to jump through some hoops and loops to solve this. And we lost about 2 or 3 days on figuring this one out and solving it. And then it dawned on me while I was solving this. That's probably one of the reasons why triggering from S3 is not supported out of the box. So I'm nearing the end of my presentation. So if you were to take away anything from this, let it be these. So one of the main things that we gained by using step functions instead of plain lambdas was observability, because of all the visualization and search features of step functions. They make it so easy to see your flow and where the problem actually is. And on the other hand, what we lost was a little bit of money, because step functions, after all, is not a free service. But in the end, the money was well spent, if you ask me. Another thing that we gained by refactoring our code and making it step function ready was that we now have tiny, fast, and highly focused functions that do just one thing and do one thing well. We lost a little bit of simplicity in the process because we went from 3 to 21 Lambda functions in total. So yeah, we did lost a little bit of simplicity, but we did gain resiliency and we became more lean. And finally, in the end, we achieved the main goal, which was a quick and simple feedback for users. But to gain this, we went from 2 to 5 AWS services, which does increase overall project complexity. And with this, I would like to wrap up. And as they say, the best is saved for last. But since my talk was last, it means that you were the best if you stayed and listened to it. Thank you very much.